Hello, welcome to the next chapter. This is chapter 11, and this is all on intermolecular forces. And we are going to discuss the types in part 1. So, less energy is needed to break these intermolecular types of bonds as compared to intramolecular ionic and covalent bonds. So these are much weaker than those kinds of bonds, but they are important. The first one we're looking at is dipole-dipole. And even neutral polar molecules can attract each other if they have little areas where there's positives and negatives kind of sticking out. So if we look at this as a molecule, it has a little positive area, and there's also a little negative area on the other side. They can attract another molecule next to it. It is a very weak attraction, but it is there. So the negative of the next molecule may have a small attraction. And another molecule coming up as well may be attracted as well, positive to negative. These can also work the opposite. They can repel each other. Two positives, two negatives will not go near each other. And so you'll get a repulsive force as well. So the closer these molecules are, the greater the attraction. Now there's 3 questions. This is question 1. The answer will be at the end. What will happen to the boiling point of a substance as the dipole moment increases? Pause to answer. The next kind of bond is hydrogen bonding. This is a strong dipole-dipole attraction between a hydrogen in a polar bond and unshared pairs of electrons on something very electronegative like oxygen, fluorine, or nitrogen. We usually use water as the example because it has two clouds, each with an unshared pair of electrons that are extra. That will attract the hydrogen on the next water molecule, and so on and so forth. These form hydrogen bonds. It is a type of dipole-dipole bonding. And it's 3-dimensional. It's hard to draw when you're using it 2-dimensionally, but you can see that these can be quite complex, the way that they're attracted to each other. Question 2, using the theory of hydrogen bonding, can you explain why ice is different than water in density? This is the second question. It'll be answered at the end. The third kind is London dispersion forces. The motion of electrons in a neutral atom can sometimes create a momentary or instantaneous dipole moment. Just the movement of electrons. We're going to look at helium as the example. Has 2 protons in the center and 2 electrons floating around in its cloud. On occasion, these 2 electrons can find themselves on the same side of the atom, creating a little area that's slightly negative and the other side slightly positive. If another molecule, another atom is next to it, it can force the other electrons to be repulsed. They will be on the other side. And you can see that the nucleus of one will be attracted to the electron cloud of the other, and you get a momentary attraction, a bond of sorts. These will allow gases to become liquids if they are forced close together. You can get a whole chain reaction. Which brings us to the third question. And the third question has to do with this little guy. So what does a gecko have to do with London dispersion forces anyway? Do you know? Here are the answers to the three questions. A little crab is going to come and he's going to give you the answers. The first question had to do with boiling points. And what happens when you have these forces interacting, these attractive forces interacting? Since the dipole attraction has gotten stronger, molecules will resist getting pulled apart. This will cause the boiling point to rise. It will take more heat energy to pull these apart to gaseous form. The second question had to do with ice and the density of ice. The hydrogen bonding in ice forces an open and orderly arrangement of molecules as they align. So the density of ice is less than that of water, which causes ice to float. This ability allows life on the planet to survive. And why? Do you know why? And the last one had to do with a gecko. Geckos are the only animal on the planet that can walk upside down on glass. Their feet have thousands of tiny hairs that can cause London dispersion forces to occur in their tiny molecules of their tootsies. These in turn cause the glass molecules' electrons to shift, causing a dipole moment to occur between the feet and the glass. In fact, this effect is so incredible that the gecko's feet actually sink into the glass a tiny amount, almost like it was a gel. The gecko is the first time that London dispersion forces was observed to occur in nature. Amazing. This is end of part 1.